So it turns out that I was looking in a related area, and I found this study from last summer. And this study was trying to also develop a diagnostic test, but for lung cancer. And essentially, they used the same exact procedure. So they got the lung fluid in the same way with that bronchoalveolar lavage, and they collected that fluid. And out of that fluid, they isolated genetic material, and they sequenced that and they called it a possible biomarker, and this could be a test for lung cancer. So I thought it was quite interesting and coincidental that the same exact procedure was developing a diagnostic test for lung cancer as was developing a diagnostic test for this pandemic pneumonia. So let's look a little bit more in detail at this test. So this is that RT-PCR stands for, it's a mouthful, but it's reverse transcription polymerase chain reaction. And the RT part refers to that we're using it to amplify RNA rather than DNA. If we were using it to amplify DNA, it would just be called PCR. Okay. Now, I'll tell you some important things about this test. So the most important thing is it's not actually testing for the virus itself, it's testing for a sequence of RNA. Now, that sequence of RNA may be present in a virus, but it also may be present in other things. And so I'll give you an example, and I think I mentioned this before, but let's say we had a person that we wanted to identify. Okay, so James, I'm going to use you this time. So we want to be able to identify James out of a crowd, and we're going to send him to Yankee Stadium to a baseball game. But we're not going to look for James's face or any other part of his actual body. Instead, we're going to use a surrogate marker just like they're using for this test. So we're going to put a cap on James's head. And now we're not going to use the typical navy blue Yankees hat because there are going to be a million people with that, right? So we got a unique Yankees hat with pinstripes on it. So it's white with blue pinstripes. And we're going to have him put that hat on and then go into the stadium and disperse amongst the crowd. And then we have a team of 10 people that we're going to send out into the stadium looking for that hat. Okay, so we do this procedure, and lo and behold, what happens is we actually find 6 of these hats. Okay, so 6 out of 10 people find someone wearing this hat. So we go and identify if any of those people are James. And it actually turns out that none of them are James, because James doesn't like wearing hats. So once he got in the stadium, he gave his hat to some kid who would have liked it, and that was one of the 6 people that we found. So you see that when you are looking for something that's not exactly the thing you're looking for, but it's something that's associated with that thing, you have to really understand the relationship between what you're looking for and that thing. So in other words, we had to ask James, will you be comfortable wearing this hat the whole time, right? And then we also have to know, did other people buy this hat, or is this a one-of-a-kind hat, right? So you can see it can be very misleading. We can get a lot of false results by using this type of method. So in order to mitigate that, and by the way, this concept was just drilled into us in medical school, that whenever you're evaluating a new test, that you need to compare it to the gold standard. And that's how you know if it's actually valid. So with this COVID-19 test, there has not been any gold standard test that this has been compared to, because the supposed COVID-19 virus has never been purified and visualized. So in other words, if we were able to take people who are ill with this pandemic pneumonia and take their lung fluid, and from that purify out a virus particle that we could identify, and once we purified that, we could actually take the genetic material right from that particle, so we know that it came where it came from. We know it didn't come from anywhere else because now we have a pure sample of only these particles. Then we would be able to have a gold standard. And so the way you would test this PCR is you would have a group of sick patients, and then you would have a control group of healthy patients. You would perform the gold standard test, so you'd be able to identify the virus out of each of those patients. And then you would compare the results of the PCR test to that gold standard. And that is really critical because it would allow you to determine or calculate an error rate, because no test is perfect. It's also very, very important that you have that control group, because that control group would not have the virus present at all and should have a negative PCR test. And that's very important in order to help you calculate these error rates. So one example of a type of error that I think we'd be very concerned about with this test, because we don't want to be mislabeled as being positive for this alleged virus and then risk being quarantined or perhaps even detained. So we want to know the accuracy. Now, there was a paper that came out where they had to estimate the false positive rate because you can't calculate it since there's no gold standard to compare it against. And they actually reported an estimated rate of 80% in people without symptoms. So what that means is if you got tested, let's say you were exposed to somebody who tested positive, or you traveled or something like that, and you want to get tested, or you're asked to get tested, there would be 4 out of 5 times that there was a positive result, there would actually be no illness. So this could be a real big problem. It certainly could vastly overestimate the number of cases and also could have a lot of consequences for you based on this quarantine situation. So just to talk generally about what the PCR test, because there's actually additional error even beyond what I've described. So what this test does is it's really just an amplification strategy. And the reason this is necessary is because we're kind of looking for a needle in a haystack. We might only find a few copies of this genetic material. And if there's only a few copies, we just can't detect it out of all of the other stuff that's in the fluid. So what this does is it's a reaction that actually replicates the strand of RNA, and it makes a copy. So it makes from 1 to 2. So you would run a cycle of this reaction, and you'd go from, say, 1 copy to 2 copies. Then you would stop the reaction and then start another cycle by adding some more materials, and then you go from 2 to 4 and repeat it again, 4 to 8, and so on and so on. And this is an exponential or a binomial expansion. And if you look at the black curve on the graph here, you'll see that's what that represents. So generally speaking, when you're using this test, you want to carry out approximately between 25 and 35 cycles in order to get enough amplification that you can see what you're looking for. If you go too much beyond that, what happens is you end up amplifying the noise. So it seems to be generally represented that the absolute maximum number of cycles that you could do and still get an accurate result is 45. And that's exactly the number of cycles that is recommended for this COVID-19 PCR test. So it's right at the upper limit. And I'm going to share this quote with you from another article about PCR. It says, "What PCR does is to select a genetic sequence and then amplify it enormously. It can accomplish the equivalent of finding a needle in a haystack. It can amplify that needle into a haystack. Like an electronically amplified antenna, PCR greatly amplifies the signal, but also greatly amplifies the noise. Since the amplification is exponential, the slightest error in measurement, the slightest contamination, can result in errors of many orders of magnitude." So this is not a very accurate test, especially when you're pushing the number of cycles to get so much amplification. Just a slight mistake can result in false positives. And I think that's what we've been seeing. So I'm going to change gears now a little bit and talk